Thank you very much for coming here. I'm honored to be selected for this award, and for various reasons, I'm doubly excited to be here. Today, I'm going to tell you a story about how I decided in the middle of my PhD track, decided to quit, delayed the quitting process by 1 day, and in that 1 day, the work I did turned into this PhD thesis that I'm going to summarize. So I'm very emotional for another reason, because the sitting gentlemen, the two gentlemen sitting in the front row are, this photograph I took from the Pittsburgh Diffraction Society webpage while I was reading about the award. And the two gentlemen are Professor Leroy Alexander and Harold Klug. And my whole PhD thesis was based on their almost 70-year-old article dated to 1948 about statistics of diffraction in powder diffraction experiments. And I am very happy that my name will be among, or will be mentioned as a follow-up work to theirs. So there is the emotional connection to my excitement and to this conference. So the motivation behind this work and why I decided to quit was that in the beginning of my PhD, we tried to simulate data, understand, try different types of things on the analysis. From diffraction data, we thought we knew how to work. But whatever we tried failed. And we decided to start over to make sure everything is under control in our simulated diffraction data. So we realized, or as we all should double check in all our work, is that extracting valid scientific knowledge from an experiment is possible only if we have repeatable data that's reliable, and secondly, if we are using the correct analysis tools to analyze that data. And these two conditions are especially important for powder diffraction experiments for obvious reasons, because a powder diffraction signature is a very complicated average over the irradiated particles. Typically, what we gain out of an experimental procedure is a bunch of diffraction peaks. And here I'm showing you a simulated diffraction peak, simulated spectra from a 3 nanometer gold particle. And I just assumed a 1 angstrom wavelength. And when I was simulating this data, I was assuming all my particles were identical to each other. I had everything perfect, a perfect detector, a perfectly monochromatic planar X-rays, perfectly known sizes and shapes in my ensemble. But generally, that's not the case. When we irradiate a powder sample that I tried to show on the right, what we sample by each individual peak here, here, and here are subpopulations which only have the interplanar spacing or the orientation with respect to the incoming X-ray beam as the common factor. So when we analyze the whole powder spectra, and out of that, if we gain a few parameters, it is so hard to match those parameters to what we actually irradiated. The problem becomes a little bit simpler if we isolate a peak and talk about that. And here, normally, the typical parameters that we get out of an isolated diffraction peak is the maximum value that is measured, the peak value. And that's usually correlated with the average coherent size that's along the direction of momentum transfer vector. Another quantity is the breadth, or how fat the measured peak is, which can be correlated to the inverse size, coherent size, again, of the average scattering domain. And Scherrer equation is the handle to relate this breadth to the inverse particle size, assuming a shape, in my case, was all about spherical particles. And the third quantity is the integrated intensity, which is typically the measure of the total particles contributing to that diffraction peak. But still, we are talking about the subpopulation of particles, which could have a distribution of sizes, a distribution of shapes, and a distribution of defects. So the problem is still very hard to solve and ill-posed. So what we decided to do was to start from the beginning, from an ideal powder ensemble, generate the ideal powder ensemble, irradiated them one by one, each particle, get all the diffracted spots, project them onto a detector, generate the ideal expected diffracted signal, and analyze this, and to see if we can really get back what we started with. This thing is what we called direct modeling in my thesis and the publications we had in the last 3 years. And I like to think about it in two parts. On the left, I'm showing you what I call the real space part of the problem, or the statistics of sampling of particles. Here, my inputs are how many particles I have in my ensemble, what's the wavelength or the direction of the X-rays that are irradiating this ensemble. And on the right, I'm showing you the reciprocal space part of the problem, which consists of the diffracted signal. But I can, tracing back all the diffracted spots from real space to reciprocal space, now can actually match all these diffracted spots to which particles they originated from. And this is only possible, as you would expect, by computational means in a diffraction experiment. This is not possible in the real world. So I'm going to be talking about the happy ideal world, which gave us very surprising results. I hope you will be also surprised. The first part will be exploring understanding the sampling statistics of particles and activated poles. And I will be talking about the classical Alexander-Klug analysis, which has been the basis of the statistical sampling process in a powder diffraction experiment. I will give the details of how we came up with the direct modeling algorithm, and I will show you results of what we got out of this algorithm by extending the analysis published by Alexander and Klug to the nanocrystalline particle regime. And finally, I will show you a comparison between what we obtained by direct counting algorithms and what Alexander Klug analysis forecast. So briefly, the basis of the Alexander Klug and Kummer analysis, which I use AKK for short, says that, let's say we have an ensemble of particles. Here, I have 3 ensemble of particles which consist of same number of particles. All particles are the same. The only difference is their orientation with respect to the incoming X-ray beam. And I use different colors to just show that they have different orientations. If I irradiate this ensemble, I get this spectra. I call it Tri1. I do the same experiment, I get another spectra. Same experiment with a different ensemble having the same properties, I get another spectra. What Alexander and Klug proposed was that if all these diffraction peaks can be matched to the amount of particles satisfying the diffraction condition at that particular Bragg reflection, then the uncertainty attached with all these individual peaks should be the same as the uncertainty of the particles that give rise to these diffracted intensity peaks. So in short, since the diffracted intensities, the signal is proportional to the diffracting particles, then their uncertainties must be the same. Which means that if we want to quantify the uncertainties in diffracted intensities, all we need to know is to come up with an expression that would give us how many particles will diffract at each HKL condition. And using that, I can just assume a binomial probability distribution and then formulate the uncertainty based on particle statistics. And they did come up with an expression of probability of diffraction by using geometric algorithms, which I will be introducing now. But before that, let me explain you what assumptions they had in their classical analysis. And I don't want to give you the impression that these assumptions were really what we read in their article. By trying everything to imitate the steps they did and the results they obtained, we figured that out afterwards. So they are actually assuming that one diffracting particle is contributing a single spot to the detector. And that detector, the probability of diffraction for each particle is linearly proportional to the multiplicity of that reflection. So if a particle is aligned at the 1-1-1 condition, assuming a FCC particle, its diffraction probability is 1/3 of the same diffraction probability if it were aligned for the 3-1-1 reflection. And finally, each diffracted spot has to contribute the same diffracted signal at the detector. This is the only way that the diffracted intensities are proportional to the diffracting particle populations. But this last term, each diffracted intensity spot contributes the same amount of signal, can be satisfied only when the intensity peaks are narrow, so that all diffracted spots are within very close vicinity of the Bragg angle. The powder sample is fairly monodispersed, so that big particles are not contributing enormous amounts of signal in relation to the small particles. And finally, each diffracted spot contributes a constant intensity. And this is only possible if your intensity profiles are Dirac delta functions. Which actually, it was the reason or the conclusion they got out of their analysis that their statistics formulation was applicable for their 6-micron particles. So my point is, are all these assumptions satisfied in a nanocrystalline regime? So that the next question is, can I use this analysis in my nanocrystalline powder diffraction experiments? So in the upcoming slides, I will be testing each of these assumptions, whether they hold true or not. So the diffraction probability term, the geometric area-based diffraction probability term that Alexander and Klug came up with can be constructed by this Ewald sphere and this isolated particle at the center. We assume a planar monochromatic X-ray beam with K vector, Ki, irradiates this vector. And if this particle satisfies the diffraction condition for a given HKL reflection, then the angle between the incoming and the outgoing beam is 2 theta b. We all know that, theta b being the Bragg angle. And this particle, its surface normal actually intersects with this Ewald sphere at this point, which I will call an activated pole. Obviously, this particle has many other poles, but only one of them will be activated at this particular orientation. So if I test many particles for their to see if they satisfy the diffraction condition or not, I realize that any particle whose surface normal is on this red dashed line, which we will call the reflection circle, satisfies the diffraction condition. But if I give it a tolerance value such that even particles whose surface normals are slightly off from the exact diffraction condition contributes a significant, substantial amount of signal, then I can actually generate this yellow band, which would conclude that any particle or any activated pole which lies on this band contributes diffracted intensity. So all I have to do to come up with an expression for diffraction probability is just getting the area of this yellow band divided by 4 pi r square. And since they assumed that the diffraction probability must be linearly proportional with the multiplicity of reflection, all you have to do is to multiply this geometric term by MHKL and you're done. So when we did this, what we came up with was this 1/2 cosine theta b d theta, where d theta was the thickness of the reflection band. So up until here, we are just tracing the steps of Alexander and Klug. What we did that was different, or was an addition to their analysis, was to write this thickness term in terms of the Scherrer broadening. which could be very significant for nanocrystalline particles. Because imagine your typical Scherrer constant is on the order of 1, 1.1, 0.8, 0.9, depending on how you define the breadth. There is a wavelength term that's 1 angstrom, 2 angstrom, something. If your D is, again, some sort of angstrom, 10 angstrom, 20 angstrom, 50 angstrom, you have significant amount of breadth, which could be 1 degree, 2 degree, that are orders of magnitude larger than typical breadths that we talk about when we have bulk powder ensembles. So, by writing the broadening term in terms of the broadening just due to the particle size and ignoring all other contributions to the broadening, such as instrumental broadening factors, what we can write for the diffraction probability is independent of the Bragg angle, but must be proportional to the multiplicity, Scherrer constant, lambda, the wavelength of irradiation, some sort of a scalar that we can define to be 2, 4, 1, some sort of multiplier, and inversely proportional to the particle size. For nanoparticles, this is quite of a good approximation to the expected breadth, because again, 2-3 degrees of breadth just from the particle size is usually much, much larger than instrument broadening contribution. And when we just put the Scherrer breadth in terms of this expression, what we came up with can call this is a modified nanocrystalline probability term. What we did, which was surprising, was to put some values, for example, 1 angstrom for the wavelength, 30 angstrom for the particle diameter, and assuming a spherical particle, 1.17 for the shape constant, we easily got probability values that were larger than 100%. So whatever orientation you have in your ensemble will be a diffracting particle, which is actually not really expected. This was the warning sign for us to dig deep and go back and count every possible surface normal and generate the diffracted signal from the particle. And this is how we do it. How we do it is we assume there's an ensemble of particles, ideally monodispersed. Everybody has the same shape, same size, all crystalline. I take one particle out of this ensemble, put it into the center, and check whether the diffraction condition is satisfied for all of its surface normal vectors. This means that for 1, 1, 1 reflection, I'm checking 8 vectors. For 2, 0, 0, I check the face normals, and so on. And this way, I can independently count how many poles will be activated, which would, in the detector plane, be the diffracted spots, and how many particles are contributing independently. And now I'm showing you the distribution of all activated poles in the reflection band, the yellow band that I showed before, from testing 10,000 particles one by one, assuming 1 angstrom wavelengths and 3 nanometer diameter. So if you test all these particles and map all their activated poles, you get this cylindrical distribution, which could be later mapped onto the detector. Here, the red spots can be mapped to a unique individual particle, which means in those cases that they originate from a particle that has only one of its MHKL vector activated. And the green spots, which are the unexpected spots, come from actually in pairs. So in that case, one particle contributes or has 2 of its surface normals that satisfies the diffraction condition simultaneously. So we try to count the numbers, which means get some numbers for the sampling part of the part 1 of the study for a few different, changing the different parameters. For example, assuming an ensemble of 10,000 particles, a wavelength of 1 angstrom, and again 3 nanometer size, what I come up with is 780 diffracting grains, but 795 diffracted or activated poles, same as diffracted spots. And if you repeat this calculation for the rest of the first 4 reflections, what we observed was the number of diffracting activated poles was always larger than the diffracted grain populations. So we decided to quantify it in a ratio, in a proportion type of way, which we call the pole activation or pole enhancement factor. It's just the ratio of the number of poles activated divided by the diffracting particle populations. And we repeated this analysis by changing the particle size, and we observed even larger pole enhancement factors. This is, as you might expect, is just the result of thicker and thicker reflection bands, higher diffraction probabilities. And also, if you go from a lower multiplicity diffraction peak to a higher multiplicity diffraction peak, you see a much more enhancement in the pole counts with respect to the grain counts. Similar effect can be observed when we keep the particle size constant but the irradiation wavelength larger. But here you see the enhancement is even more. So you have almost 36% more 311 activated poles than diffracted grains. And so we see that increasing the wavelength and decreasing the particle size do not end up with the same amount of enhancement, but they are resulting in a similar effect. If we repeat this many, many times, and for various particle sizes, you see that most of the enhancement of the poles with respect to the grain counts happens in small particle sizes and for high multiplicity reflections. For all of these reflections, as the particle size goes up, you lose the enhancement, and then there will be a one-to-one correlation between pole and diffracting grain counts. And for high multiplicity reflections, you need a much higher particle size to get this one-to-one relationship with respect to the lower multiplicity reflections. If we come up with this factor that we call d-min, which means the particle size that results in a 100% diffraction probability, and scale all these particle sizes in a non-dimensionalized way, we can then combine all these plots into one plot, and as you see, it shows an exponential decay with respect to the particle size. If you have an increase in particle size, you lose this pole enhancement effect in an exponentially fast way. So another fancier way to plot the pole and grain counts is to show the ratios. So here on the left, we are looking at the activated pole ratios at 2 different reflections, 200 to 11, 220 to 111, 311 to 111. And normally, we should expect the multiplicity ratio to come up. And this is actually more or less what we obtain. Here, each of these points are a result of 10 independent simulations, and the uncertainty are within the bounds of the marker size. So we see that the multiplicity ratio is more or less conserved when we look at the activated pole populations, but on the right, when we look at the diffracting grain populations, we see a lot of deviation as the particle size gets smaller and the yellow band thickness gets larger, which means that for large particles, when the S over D is small, then the probability of diffraction from the grain point of view is really proportional to the multiplicity of reflection. However, this is not true for very small particle sizes. What's interesting is the ratio of the activated poles are still following the multiplicity ratios. So to summarize the first part, I should say that area-based diffraction probability term that was proposed by Alexander and Klug is not directly applicable for grain statistics when the particle size is in the nanometer regime. The implicit assumption in the classical analysis that one particle results in a single diffracted spot is unjustified and not valid when the particle sizes are small, nanometer regime. For nanocrystalline particles, direct transition from particle populations to diffracted spots is not possible because we lose the one-to-one relation as the particle size goes to smaller values. And the multiplicity factor is actually becomes the size-dependent effective multiplicity term, which is a function of the Paul enhancement effect. And so our conclusion is the classical analysis is probably a special case, a limit of large particle results for the statistics of particle sampling in powder diffraction experiments. So up until here, I wanted to convince you that the assumptions related to the particle sampling are not justified. And from this point on, in the second part of my talk, I will try to explain or show how the assumption of all diffracted spots contributes the same intensity is also unjustified when the particle size goes to the nanocrystalline particle regime. But there are multiple reasons why this is so. So in my bigger picture, now I'm going to be talking about how the diffracted spots are sampled and how the diffracted intensities can be related to the spot distribution and later on the diffracting particle distributions. The outline consists of an explanation of how we calculate the diffracted intensities based on the activated Paul distributions. I will introduce an updated Lorentz correction term. That's just a curvature correction term that we actually use in bulk powder analysis also. And then I will finally conclude by a comparison of the statistical uncertainties in the diffracted intensities and diffracting particle statistics in the classical and in the direct modeling nanocrystalline regime. So, how do we model the diffracted intensities? Once we have the activated Paul populations, this means that we actually know how each activated Paul is away from the exact Bragg condition. If I know that, I can easily map it to a detector plane. And here I'm showing you how these spot populations look like on the detector plane. Here, again, the green spots are coming from in pairs from the diffracting particles, and each red spot can be matched with a unique different particle. And the red dashed lines are just showing the position of the exact Bragg Scherrer ring. So after I obtain the angular distribution of the diffracted spots, all I have to do is to match the intensities to each of these spots and then sum them up. And I can do that based on Patterson analysis. What Patterson did in his 1939 article was to formulate that the characteristic rocking curve of an isolated particle is actually proportional to the square amplitude of the particle's shape function. So for regularly shaped particles, these shape functions are actually analytically calculated, and that's what we did. For our spherical particles, the Patterson function is a form of a sinc square function. And by multiplying the number of spots at a given deviation angle and summing all the contributions from each of these spots, what I ended up with is this nice diffracted profile where I can now separate the contributions coming from particles that are contributing multiple spots, single spots, triple spots, or I can come up with a total signal, just like what we observe in the realistic experiment. So after we obtain the diffracted intensities from our ensembles, we need to come up with an analysis. What we did was to first fit the position and breadth of these peaks. But what we observed was as the wavelength increased or the thickness of the reflection band increased, we saw that there was more and more shift away from the expected Bragg positions. And this is purely an effect of the bias, the geometric curvature bias of the Ewald sphere. for negative deviation angles from the exact Bragg condition, you have a longer circle, so you have a larger area. And so that the probability of activated poles or diffracted spots is larger in negative angles versus positive angles. So we needed to come up with a correction factor, and this is typically done by the Lorentz polarization factor, which is a combination of the polarization effect and the geometric effect. And typically, the correction is done in the intensity profiles. But in our case, since our intensity profiles are a function of some analytical formula times a statistical parameter, we only needed to correct the statistical part of this equation. So all we needed to do was to straighten up our diffracted spot populations. We tried two different ways to make them straight. The first one was what I call the CT1, correction term 1. We first divided the row, which are shown to be these black spots, the row of diffracted spot counts by dividing them by cosine theta b. What I obtained was this red population distribution. Here, yes, we were able to get some straight spot distributions, but we couldn't preserve the total number of spots, so we needed to divide it, multiply it by the cosine term, and now our new modified Lorentz geometric term happens to be cosine theta divided by the cosine of the Bragg angle, and this theta is just the deviation in the reflection band from the exact Bragg condition. So after we correct our intensity profiles, now we can compute the diffracted intensities, integrated peak intensities, and try to match them with the real space parameters. And here we are looking at the results from 10 runs of diffraction simulations where I have 10 to the 4, 5 times 10 to the 4, and 10 to the 5 number of particles in each ensemble. So each of these boxes are the average counts from 10 independent simulations. And the blue part of the table refers to the values I get from the 200 reflection. And on the right, we look at the results from the 311 reflection. I wanted to show the minimum and maximum multiplicity reflections to show how different they are. And there are some things that we expected to see. Of course, when you increase the number of particles in your ensemble, your diffracted signal increases, your particles participating in diffraction increases, and obviously the diffracted spots that are captured by the detector increases. However, what is not so easily seen in the table can be easily plotted and communicated if we have two axes. So here on this plot, I'm showing you sampling parameters, which are diffracting grain populations, diffracted spot populations on the left, and on the right, we're looking at the diffracted intensities, integrated intensities, and maximum intensities. And my horizontal axis is multiplicity, which is parallel to the direction of increasing pole enhancement. So as you see, as the multiplicity of reflection increases, the deviation from the diffracting grain populations from intensity parameters increase more and more, which means for high multiplicity reflections, you have far more difference between real space and reciprocal space parameters, which means that the intensities are not really linearly proportional with the diffracting grain populations as Alexander and Klug proposed. If I compute the relative uncertainties from the table I just showed you, and all I did was to divide the standard deviations by the expected counts, what I see in, again, these two different reflections for different ensemble sizes is that in none of the cases, the intensity uncertainties are equal to the diffracting grain uncertainties. And this is not true for the 200 reflection, not true for the 311 reflection. So since the intensity, diffracted intensity signal is not proportional to the grain counts, the uncertainties are also not equal. But I also said that there is one more reason why the two are not really comparable. And the reason is, let's go back to the particle sampling. When we have this ideally randomized monodispersed particle sample, and if we select one of these particles to check whether that satisfies the diffraction condition or not, this experiment has only two values. It's a discrete counting process. It's a discrete probability distribution. One particle either diffracts or doesn't diffract, which means it's either 0 and 1. However, when we go back and try to assign intensities, which means how the intensity is sampled is not really a discrete phenomenon, especially for nanocrystalline particles. If this particle is not a diffracting particle, its intensity contribution is 0. But what if it satisfies the diffraction condition? Then the next question is, where does it satisfy the diffraction condition? Is it close? Is it really at the exact Bragg condition, or is it a little off? Or is it way off? So it only contributes 1% of the peak intensity. And that is why intensity statistics is not really a discrete statistics phenomenon, which cannot be modeled by binomial distribution. Instead, it's a continuous distribution, and we should just use integrals. How that translates to a real experimental setup, I wanted to put a simple sketch for that. And here we are looking at the rocket curve profiles of three different particles. One has 10 nanometer size, this black one. The other one has 100 nanometer size, and the last one is 3 micron. And as we all expect, the 3 micron particle has almost like a Dirac-Data function as its rocket curve profile. However, the 10 nanometer particle has lots of peaks. So assuming we have this world's simplest detector here measuring the intensities, what we see is that all of the intensities are actually recorded by the central pixel when the particle size is 3 microns. But when it's 100 microns, I still get all my intensities recorded by the central pixel, whereas when the particle size is 10 nanometer, you see there's almost 3 to 7 pixels that collect all the intensities, and each of these detector pixels assign a different value, which means that all of the diffracted spots do not contribute the same constant value to the diffracted signal as proposed by Alexander and Klug. But then how do they relate? And this table actually published fresh, and I will give the references in the next slides. Here I'm showing you how the total intensities, the standard deviation in total integrated intensities and their uncertainties are from a simulated experiment assuming 3 nanometer particle size, 2.29 angstrom irradiation wavelength, and an ensemble of 100,000 particles. Again, all of these quantities were computed by running these simulations at least 10 times. And here we are looking at the uncertainty ratios of diffracted intensities with respect to the diffracted spots. And again, the same ratio with respect to the diffracted intensities by the diffracting grain populations. And for all of these reflections, we see that the uncertainties in the intensity space is close to twice as much as the real space uncertainties. So this is another realization that the uncertainties are, again, not the same. And uncertainties in the intensity space is always larger than the real space uncertainties. And for higher reflections, we see that the uncertainties in the grain with respect to the uncertainties in intensities are an order of magnitude different. So my summaries are, the classical definition of the Lorentz geometric correction term is not directly applicable for our case, but it's a similar cosine theta form. Due to the loss of linearity between diffracted grain populations and diffracted intensities at high reflections, the relative uncertainties cannot be related in the diffraction and in the intensity and real space parameters. The selection process behind particle sampling and diffractive intensities are different. The intensity statistics is a continuous statistics phenomena, whereas particle selection is a binomial distribution. And due to the continuous behavior of expected intensities, diffractive intensity statistics cannot be represented by binomial distribution. And my final points are for nanocrystalline powder samples, population of activated spots are always larger than population of diffracting grains. And uncertainties in the intensity space are always larger by multiple orders than the uncertainties in the real space parameters. The statistical models dictating the expected values of sampling and intensity parameters in two different spaces are different. They cannot be related when the particle size is in a nanometer regime. And the only case where the uncertainties in the intensities and diffracting particle spaces are equal happens in the Bach parameter regime, which was actually the focus of Alexandrian Kuluk analysis. So we had 3 publications that I tried to summarize in this talk, which were published in 2014, 15, and 17. And I tried to summarize 5 years of my work in this talk, and so I would like to thank Columbia University, my department, my advisor who is here, Professor Cevdet Noyan, and I thankfully acknowledge the grant from Department of Energy, which financed my PhD. And my last point is, do not give up today. You can always do it later, and thank you.